Today I want to talk to you about a revolutionary technology that has been reshaping the aircraft industry, 3D printing. 3D printing has made construction of small and complex structures more convenient. It works by adding materials layer by layer based on computer design, allowing for a development and customization of virtually any type of design. One of the greatest advantages of 3D printing is its cost effectiveness. It allows for a low cost creation of components without the need of expensive toolings and mold. This makes it ideal for producing high quality customized structures in minimal quantities, perfectly suited for the specialized needs of the aircraft industry. This technology has vast application in our field. I will give you an overview of 3D printing technologies and the specific uses in aircraft manufacturing and maintenance. We'll discuss the materials, elements and components developed for aircraft applications along with their unique properties. We'll explore the various types of 3D printing, its advantages, applications, the limitation within the context of aircraft industry. So let's dive into the world of 3D printing and see how this cutting-edge technology has been transforming the way we build and maintain the aircrafts. 3D printing is also known as additive manufacturing. It is a set of technologies used to create prototypes, patterns, tooling components, and physical models. This is done using data from computers, 3D scanning system, and other advanced digital sources. Unlike traditional manufacturing, which involves subtracting materials like lathe, where you grind or drill from a metal piece, here in additive manufacturing, builds object layer by layer. Whether it's powder, sheet metal or liquid. This method can produce parts that are difficult or impossible to create using other technologies. Several additive manufacturing technologies are in use today, including 3-dimensional printing, selective laser melting, stereolithography and fused deposition modeling. In recent years, the use of additive manufacturing technologies by engineers, designers and other professionals has been steadily increasing. There are various additive manufacturing processes which can be classified based on their power delivery system, energy sources. For instance, direct metal laser sintering is a wire-based system used to make parts from metal alloys. This process is a very high advancement of powder metallurgy, a technique that produces powdered metal parts using pressure and temperature. Products made using wire along with arc additive manufacturing, also known as WAM, are high quality and often preferred over conventional welding methods. WAM can be applied to a wide range of metals provided they are in wire form. Any metal then can be welded using traditional methods such as stainless steel, nickel-based alloys, titanium and aluminum alloys can also be used with WAM. Another method that is powder bed fusion, also known as PBF, is used to fuse and melt powdered material together. This technology employs a laser or an electron beam to achieve the fusion. Within the powder bed fusion, there are several printing techniques including electron beam melting known as EBM, selective heat sintering SHS, and selective laser sintering SLS. These techniques can utilize a variety of materials like ceramic, plastic and metals. The SLM printing technique on the other hand is used to manufacture product from any material. EBM is becoming a high standard replacement for the laser melting technology and is also used to repair and manufacture turbine blades of the engine of the aircraft. Along with powder bed fusion, directed energy deposition and other technologies, EBM can be used to create structural parts for aircraft or smaller mechanical components also. In the realm of solid state welding, friction stir welding allows, also known as FSW, allows for welding without melting the workpiece material. This method uses a non-consumable tool which unlike the traditional welding where the tool that is used to weld is slowly consumed by the process. Here the stacks of weld plates are lap welded and then friction stir welded layer by layer to form a product. This technique is particularly useful in the aircraft industry for manufacturing of say longerons stringers or stiffeners, and wing spars. Among the various additive manufacturing processes, only a few meet the stringent requirements of aircraft industry. The most widely used additive manufacturing process in the sector are EBM, SLS, WAM, and SLM. The first commercialization of 3D printing process, also known as stereolithography, was developed by Chuck Hull in 1983. The idea came to him while he was building a tabletop using a UV light to cure layers after he has laid them to get a 3D structure. Essentially, 3D printing also involves adding materials layer by layer to build physical models. But here we are doing using 3D model data. To create a product with a 3D printer, the design must first be created in a 3D CAD tool. Also like AutoCAD, Fusion 360, CATIA and SolidWorks, etc. To create a product it must be in a compatible file format of the printer. 3D printer offers high customization in product design, enabling the production of components that can't be made using conventional manufacturing techniques. One of the key benefits of 3D printing is that it allows the creation of delicate components with minimum material waste, where you can get as many thin layers or layers where it is not possible for other machining tools to remove the materials from that area to get the structural joint. So it is one of the main advantage, and the other thing is that it has a lower manufacturing cost and reduced production time. The basic concept behind 3D printing technology is stereolithography, where a liquid photopolymer surface is exposed to concentrated UV light rays. The UV light beams draws each layer of the object onto the liquid surface, solidifying it where the light strikes. The computer model of the component is sliced into many fine layers using advanced CAD/CAM softwares, and the 3D printer builds the components layer by layer that has been sliced from the original CAD model, resulting in a final product. Today, 3D printing technologies can produce objects from a wide range of material, including conventional thermoplastics, metals, graphene-based materials, and ceramics. This technology offers numerous advantages such as low cost, reduced time consumption, and decreased manufacturing complexities. 3D printing has been widely adopted globally, especially in manufacturing and research and development sectors. It's recognized as one of the most powerful and flexible technologies in advanced manufacturing. 3D printing processes are classified based on the fusion of matter at the molecular or atomic level, using electron beams, ultraviolet lights, lasers, or thermal energy, and the properties and physical state of the primary material, solid, powder, or liquid. There are 7 types of 3D printer commonly used in the aircraft industry: digital, EBM, SLS, FDM, SLM, laminated object manufacturing known as LOM, stereolithography, and digital light processing. Now let's delve into the different types of 3D printing. 3D printing has been developed in various ways, each with different modules. It's challenging to determine which technology and functions are superior because each has its own specific applications based on customer requirements. 3D printing technology isn't just limited to prototyping, it also encompasses creating a wide range of products. Several types of 3D printers are used in aircraft industries depending on the specific parts and components that needs to be manufactured. Some research-based aircraft industries use particular types of 3D printer, adjusting the filament and infills used in the printer to meet their specific needs. We'll discuss the infill used in 3D printers in an upcoming section. Before selecting any type of 3D printer, it is important to understand the filament material used to manufacture the parts and components. Additionally, you should have prior knowledge of the sizes, types, and accuracy of the parts and components that the 3D printer will produce. The aircraft industry holds some of the highest standards for component performance. Aircraft parts are subjected to extreme temperatures and chemicals while in use, and they must be also lightweight, as much lightweight as possible. Any individual component failure can lead to a full system failure of the aircraft, which is unacceptable given this aircraft carries passengers and cargo. Therefore, precision in component manufacturing is critical and the reliability is of utmost importance. 3D printers are employed in the aircraft industry to achieve extremely high accuracy in parts and components. The types of 3D printing used to manufacture metal-based components and parts for aircraft include direct metal laser sintering (DMLS), electron beam melting (EBM), selective layer melting (SLM), and stereolithography. For manufacturing of polymer and composite based aircraft components and parts, the types of 3D printer used are selective laser sintering (SLS), stereolithography, digital light processing DLP, fused deposition modeling FDM, and material jetting. According to ASTM standard F2792, 3D printing technologies are categorized in 7 distinct categories. Now let's talk about binder jetting technology. Binder jetting is a 3D printing process where the binding liquid agent is used to selectively deposit on powder particles, fusing them together. This method is commonly used in rapid prototyping because it allows for the creation of layers on spread powder quickly and efficiently. Binder jetting technology is faster, cheaper, and simply compared to all other methods, making it suitable for printing large-sized objects. Then direct energy deposition (DED). DED is a precision printing process used to add or repair additional materials to existing parts. This method ensures high quality production with precise control over grain structures. DED is usually employed with metal based hybrids and other metals. It also utilizes various ceramics and polymers, either in powder or wire form. Example of DED technology includes laser deposition and laser engineered net shaping lens. Then material extrusion. Material extrusion is another type of 3D printing technology that is versatile for producing multicolor and multi-material prints, including food, plastics, and even living cells. Fused deposition modeling is a popular method under material extrusion. Constructs parts by extruding thermoplastic filaments layer by layer from base to peak. FDM printers are generally affordable and widely used due to their simplicity and versatility. Material jetting utilizes an inkjet printing process where liquid photoreactive material is deposited layer by layer onto a platform using print heads. The deposition method varies based on the printer technology and can employ either a drop-on demand, that is DOD, or continuous jetting principle. Then we'll talk about powder bed fusion. PBF encompasses several 3D printing technologies like selective heat sintering, selective laser sintering, and electron beam melting. These methods produce powder materials together layer by layer to create solid objects. Sheet lamination is another 3D printing process where thin sheets of materials are bonded layer by layer to form a single piece. Sheets are fed through a system of rollers for bonding, making this process cost effective and conductive to material handling and recycling. Full color printing is also possible using sheet lamination techniques. Examples of this method include ultrasound additive manufacturing, that is UAM, and laminated object manufacturing, that is LOM. The last technique is wet photopolymerisation. It is widely used in 3D printing that involves curing photoreactive polymers using ultraviolet rays or lasers. Key factors such as exposure time, powder supply, and wavelength affect this process. Liquid materials harden when exposed to ultraviolet light, allowing for detailed products with high surface finish. In aircraft application, it is crucial to use high quality materials that meet stringent specification to produce reliable products. Suppliers and end users adhere to strict controls to ensure these materials meet specified requirements. procedures and agreements. Materials commonly used in 3D printing include aluminum alloys. I'm talking about the aircraft industry. Aluminum alloys, titanium alloys, ceramics, polymers, steels of various types, and metal composites or hybrids. These materials are adeptly utilized in additive manufacturing to create fully functional parts. Depending on the additive manufacturing techniques employed and the physical properties of the material, objects can be constructed with layer thickness ranging from 20 to 100 micrometer. 3D printing materials are categorized into four main types based on morphography: plastic filament, powder material, liquid photosensitive resin, and low melting point wire material. These materials are chosen based on criteria such as weight, structural reliability, surface accuracy, wear resistance, density, thermal stability, and structural strength. In aircraft industry, two alloys that are popular importance are titanium and titanium, that is Ti6Al4V, and other is Inconel 718. It is a nickel based alloy. These alloys are favored for their excellent oxidation, corrosion resistance, damage tolerance, and tensile properties. Polymers are also extensively used in 3D printing aircraft components. For example, carbon fiber reinforced polyamide 12, that is also known as carbonamide, glass bead filled polyamide 12 powder, that is the code name of it is PA3200GF, then aluminum filled polyamide 12 powder, alumide, and flame retarded white polyamide 12 powder, that is PA2210FR, are commonly used with selective laser sintering. In fused deposition modeling, polymers like polyphenol sulfane, pig polyarylethar ketone, and nylon 12 are utilized. Various metals and alloys are also used in 3D printing for aircraft parts, such as martensite hardenable steel and aluminum alloys. Both processed with direct metal laser sintering technology. Infill is another critical aspect of 3D printing, referring to the repetitive pattern used to occupy the space inside the 3D printing objects to fill the empty space and give it structural rigidity. It supports structural integrity, weight distribution, and printing efficiency. Choosing the right infill pattern density and orientation is crucial for ensuring the strength and stability of the final product. One of the key benefits of 3D printing in aircraft industry is the reduction in material usage, leading to fuel savings. Components such as engine parts, wings, fuselage, and empennage can be manufactured or repaired quickly using 3D printing technologies, which is crucial given to frequent need for replacement due to operational wear and tear. 3D printing facilitates rapid manufacturing, prototyping, tooling, enabling efficient production of spare parts and components and maintenance department. Major aircraft manufacturers are increasingly adopting 3D printing technologies for its versatility and efficiency. With advancements, the future of aircraft engine production may require only a 3D printer, design data, and a small team of engineers, significantly streamlining the manufacturing process. Although the 3D printing market in the aircraft industry is still developing, projections indicate substantial growth and benefits by 2025. This growth highlights the expanding role of 3D printing in aerospace and underscores its potential to revolutionize aircraft maintenance and manufacturing. It offers numerous advantages, yet it also comes with some limitations compared to traditional manufacturing methods. In the aircraft industry, the benefit includes strength to weight ratio, significant reduction in component weight, ability to consolidate multiple parts into fewer assemblies, rapid manufacturing times, low customization cost, reduced manpower requirements. However, one of the primary drawbacks is the size limitation of products that can be produced. For instance, machines like electron beam melting typically have constraints such as maximum diameter of 350 mm and height of 380 mm, limiting the size of components that can be manufactured. So currently 3D printed parts are used in very small parts that are used either in engines or in joysticks or other areas, but it is not used to create a whole large part such as wing or any other thing. Increasingly, this limits large-scale production remains a challenge. Another issue is the surface finish of 3D printed products, which may require additional post-processing due to high surface roughness, because the layer is deposited, the material is deposited layer by layer. It needs to be polished before using. Additionally, the speed of the production can be slower compared to traditional method, because in traditional methods bulk manufacturing is possible, whereas in 3D printing only one part can be manufactured at a time. Although this is partially offset by the ability to achieve near net shape directly from the printing process, conversely, challenges include limited material availability, restricted build volumes, the need for post-processing, high cost for large volume production, reduction employment in traditional manufacturing roles, lower tolerance in part dimensions. Furthermore, certain 3D printing methods may result in layered structures that can delaminate under specific stresses, particularly notable in techniques like fused deposition modeling. Additionally, intellectual property concern arise because 3D printing enables the creation of exact replicas. Just by scanning someone else's product, even I can get the 3D scan of it and can print the same exact model from the CAD data, potentially leading to copyright infringement issues with when counterfeit parts are produced. Despite this limitation, 3D printing technology continues to evolve, addressing these challenges and expanding its application across various industries, including aerospace. The future of 3D printing technology in the aircraft industry holds promising advancement in scaling up production and accomplishing larger dimensions required for future application. This technology is poised to leverage various material alloys to enhance strength, reduce weight, and offer innovative solutions for aircraft components. Looking ahead, 3D printing could potentially venture into nanoscale printing, using different types of nanomaterials, enabling the creation of complex objects suitable for space programs and aerospace industries. Manufacturing entities like SpaceX and NASA are actively exploring 3D printing on a large scale for developing habitats and infrastructure on Mars. Numerous future developments are anticipated in 3D printing technology and its applications within the aircraft industry, promising to revolutionize manufacturing capabilities and advance aerospace engineering. The aerospace and defense industries have been early adopters and strong proponents of 3D printing, paving the way for its significant growth. As early as in 1989, the aerospace companies began integrating the cutting-edge technology, including a substantial advancement over the years. By 2015, the aerospace and defense sectors alone contributed to 16% of the global revenue of the 4.9 plus billion $3D printing market. This presentation has provided a comprehensive overview of the additive manufacturing technologies, specifically focusing on its application in the aircraft industry. We discussed various types of 3D printer and the specific printing techniques they employ. The materials used as filaments for manufacturing different aircraft components were also detailed, highlighting their properties, applications, and manufacturing processes. Additionally, we also explored the diverse application of 3D printing in the aircraft industry, noting its limitation. Looking ahead, There is a strong belief that 3D printing will continue to evolve, enabling the production of larger parts on a larger scale with enhanced materials. In conclusion, 3D printing technology holds immense promise for the future of aerospace manufacturing, poised to revolutionize how aircraft components are designed, produced, and maintained.